Chiamo Pim Van Pelt. Hi Pim. Sta intanto che sale sul palco. Prego Pim.
Oh, sorry.
Thank you very much
Hello.
for being here. I know that you drive a couple of hours for be here, so thank you again.
You're
And here's the sign for the...
It's a very important step here.
Yes, that's the right way. So, VPP, it's all yours, my friend.
In a minute. So I need you to help me because there's two really big lights on me. I always take a selfie before, and it's going to be a very black selfie. So if you could grab a cell phone or two and shine me a light as if you're at a concert, that would be fantastic. I'll grab the clicker and start, giving you just a second to do that. Otherwise, there's only this guy in the front. Okay, so I'm sorry that this has to be in English. It is a beautiful language you speak, except I don't, so that's problematic. All right. The clicker. There's also one other thing. There were two slide decks. One is a little bit longer than the other, and we're already running late, so permit me to run into the break. All right, here we go. 2 lights, 3 lights. All right, it's going to be good. Thank you very much. Okay. My name is Pim. I've been a member of the RIPE community for a while now, since 1995 or so. That's when I started in networking. 1999 was my first RIPE meeting. You can reach me at pim@ipng.nl. I sound American, I'm not. I'm Dutch. But I live in Switzerland, and I've been there for about 18 and a half, 19 years, so you can also reach me at theobligatory.ch. In the pandemic, I got bored, so I incorporated ipng.ch into a rather small company. We are a developer of software routers, fully open source, but very fast, using DPDK, RDMA, and vector packet processing. Tiny operator from the town of Bruttisellen in Tudi. Nobody knows of Bruttisellen, even the Swiss, so don't worry about it. But this one is maybe a little bit easier for you to follow. We operate a ring in Europe. We appear on the flap, except for us, the L is not London. It is Lille in the north of France. But I think it counts because it starts with an L. We have about 2,200 adjacencies or so, which makes us, ironically, the number 3 best connected ISP in Switzerland. And we acquired a 4-digit AS number to tout from 6Access, if you've ever used this stuff. I know that there are several folks here who ran a 6Access server back in the day. So an intro on vector packet processing. It's an open source data plane that runs completely in user space on Linux. Also FreeBSD these days, provides super fast networking using libraries like DPDK and RDMA and VirtIO and VMXNet if you're VMware, easily exceeding 100 million packets per second and 100 gigs. In fact, a terabit per second has been done with this data plane on commodity PCs, just a normal Dell or HP, what have you, computer running Linux, Ubuntu, Debian, or even Red Hat. So I've been talking about this for a while. I started contributing to the project in 2021, making some changes to the Linux control plane, which allows VPP to use common software in the control plane, like, say, Bird or FRR or OpenBGPD. This talk is about my own ISP and how I moved from a backbone that had all sorts of /31 IPv4 addresses on point-to-point links, which is, of course, sad if you only have a /24 these days, and I moved it to one IP address per router only. So first I want to show you real quick how you interact with VPP. There's a binary called VPP-CTL, and here you can see that I've created an interface in Linux called ICE0, plumbed from the data plane interface called 100 gigabit Ethernet 400. So that thing then exists in Linux, and you can manipulate it like any other interface. You can give it an MTU and some IP addresses, maybe create a sub-interface, VLAN tag 101, call it IPNG, give it some IPs and some default routes as well. And then you can ping, oh wait, this is no-nog, because that's a different presentation. You could also ping ITnog, I guess. All right, so IPNG also pings with IPv6 here. Let's move on after that. Okay, so Babel. Who knows Babel? And I need to squint through the lights here. I see maybe 5 hands. Don't worry about it. I also didn't know Babel. Babel is an IGP, similar in a way to ISIS and OSPF. It's meant to build mesh networks over wireless links, but it also works in wired. And has some really cool features that I found. So what I'll do here is I'll try to get Babel to work with VPP, and VPP did put up a fight. So let's see what happens here. A bunch of screenshots. First, Babel is turned on interfaces that start with an E, so E star. And I'll turn on IPv4 and IPv6 and use what is called an extended next hop, which makes it use IPv6 for all of its next hops, including the IPv4 ones, which is kind of fun. So the interface E1 quickly comes up and starts speaking Babel, and it forms an adjacency with a router on the other side of E1, which you can see there. So that works. And then learning really learns a bunch of IPv4 loopback addresses and a bunch of IPv6 loopback addresses and this /60 supernet. And for IPv6 routes, you can see pretty normal that 200::1 goes to some link local address on E1, which I've learned. But for IPv4, this is something kind of cool. An IPv4 next hop using IPv6 to resolve the Ethernet address. Now, who knows if that was possible? Again, it's super hard. I see 2 people, but there may be 20 more behind them on account of the lights. Okay. So you can indeed set an IPv4 address with an IPv6 next hop, and the other way around as well. So learning on the fib, it's easy to learn with Bird, but putting this into the fib means programming VPP to use this in the data plane. And that works as well. You can see here in the light blue that IP address 10.1 is found on IPv4 via an IPv6 next hop. That's not a bug, that's a feature. But it didn't work, though, because when I try to ping, say, this 10.1, and I show a trace on the VPP data plane, it's dropping all of the traffic because it's saying, hey, there's no IPv4 enabled on this interface because it doesn't have an address. Okay. So the first thing I do is just forcefully enable IPv4 on this interface using that API call there. And then forwarding works. That's cool, I can ping, but traceroute doesn't. And that's a little bit disappointing, not so much because of the traceroute itself, but because of what that represents. These intermediary hops cannot send any IPv4 ICMP, so they won't do path MTU and things like that. All right, so then my second try is to set unnumbered on these interfaces in VPP, and this is a feature that you'll find as well in Silicon merchants. You can borrow an IP address from another interface and put it on this interface, which itself doesn't have its own IP address. Cool, so ICMP now works, that's nice, but forwarding broke because now it's trying to ARP again on these interfaces. And it turns out, until now, VPP would never respond to ARP requests that were not on link. So what that means is, if you're in a /29, all of the 8 IP addresses might ARP me, and I will respond because I am in that /29. But if I have a /32 only, I won't respond because nothing that might ARP me is on my local network. And that's the error in red that you see. So my third and final attempt is to set unnumbered but inhibit the propagation of those addresses to Linux. So here you'll see E0 and E1 don't have the IP address anymore. They're only link local. The routes all work, and the traceroute works. And so in the end now, you'll see ICMP has responded from the loopback address on all those machines from VPP 0 on the left-hand side to VPP 3 on the right-hand side. Okay, so that worked, but I don't use Babel. This is more of an academic exercise. I use OSPF, which I think most people would use unless you're diehard and you use ISIS. Okay, so there is an RFC 5838. It's an absolute terrible piece. I don't know how this ever came through the IETF. So it said support multiple address families with OSPFv3, where OSPFv3 still uses IPv6 to find its neighbors. And then it says, and I'll quote as I start facepalming, although IPv6 link local addresses could be used as next hops for IPv4, which is what I would like, it's desirable to have IPv4 next hop addresses, which I think is reasonable, and IPv4 will therefore be advertised in the link local address field in the link state update, which means we'll place the IPv4 address straight into the IPv6 field and zero out the rest of the bits. So that means you can never use IPv6, and they should have said, instead of could be used, can never be used, because that's what ended up happening in practice. But Andre from the Bird team had a very clever solution to this, which is not even a hack, and it's still fully RFC 5838 compliant. He added a function in Bird called update loopback adder, which scans all of the interfaces, preferring host addresses, which would be /32, or otherwise OSPF stub area addresses, or otherwise any IPv4 address we might find. And then we use that address and stick it in that field, which is meant to be an IPv6 address, but sure, RFC 5838 turns that into an IPv4 in the IPv6 field. And then we learn all of our routes with RNF on link, that's a bird implementation detail, from our /32 neighbors, which inform us that this is not in our own network, right, this /32. So this is now a match made in heaven for me, because this bird commit makes all these neighbors on link as /32s, and the VPP commit that I made adds the ability for VPP to answer these ARP requests, and then the Linux control plane change that I made will inhibit these unnumbered interfaces that I was using before with Babel. So this now allows for exactly one IPv4 and one IPv6 address on a loopback. Everything works, v4 trace routes, v6 trace routes. And as a bonus, because we now use only one address family for the adjacencies with both v4 and v6, I can use one BFD session instead of two. So what that looks like real quick is this. The light blue there says to disable the sync of unnumbered interfaces. So I'll add an IP address and a v6 to loop 0, and then I'll make E1 and E0 unnumbered off of loop. So you see here in Linux side, the addresses don't appear. These are still only link local. And I'll turn on BFD. So then for the OSPF configuration, it's actually very simple. The IPv6 one is already there. It's still v3. But in light blue, you'll see there that the thing called OSPF4 is a version 3 OSPF using IPv6 for the transport. So adjacencies form, and the only difference here is now I see adjacencies at link local on these interfaces for both IPv4 and IPv6 address family. And I can learn IPv6. That's very straightforward. This worked before and it still works now, but for IPv4 it's a little bit different. Here I'm seeing 10.3 with nexthop 10.3 on link, which informs me that I must ARP out of my network for it. And all of these routes that I see in the routing table are also marked as on link. That's cool. Trace routes now work. This trace route with IPv4 at MTU 9000 will see a response from all the intermediary routers from their loopback address, because that's the only one they have. And for IPv6, it obviously already worked. So I thought maybe I'd roll this out in my tiny basement ISP IPNG networks AS8298. And what that looks like is this. Another really cool thing that VPP has as a software solution that some of the merchant silicon vendors will not be able to boast. Here we go. So in the beginning, each of my routers has a loopback address. And it also has all these /31 point-to-points, from one router to the other. My upgrade plan is now to update bird with Andre's change, and also update the VPP data plane with my change. And these are obviously intrusive events. The data plane will go down briefly. Then rename what used to be the OSPFv2 OSPF4 into an OSPF4 old, and then create an empty OSPF4, which will be OSPFv3. And I know I say v3 and v4 a lot. So then I'll move one by one all these interfaces from the old OSPF to the new OSPF, and then when it's empty, I can delete OSPF4 old, and everything looks great. And at the end of this, I will have each router taking exactly one loopback IP address. This comes from my bash history. This is the upgrade for a router called DDLN0 in some colocation site somewhere. The first command there prepends 1 and 0 to all the OSPF costs, right? So if they were 20 before, they're now 1020. And I'll birdc reconfigure. So we're draining traffic off of all the links. Then I'll rename the protocol that was OSPF4 to OSPF4 old. And I'll download a bunch of packages. Then I'll enter the data plane network namespace, and I'll kill VPP with -9. Depackage installed the Debian packages for VPP and as well for bird, and then restart everything again. And I don't know, like normally when I do this on a Cisco, an IOS-XR, or a Juniper, this takes like forever. But it does not take forever here. 92 seconds later, the data plane is up, fully converged in the DFC routing again. which is definitely faster than most merchants would do. And I see these adjacencies in the OSPF4 old, which was my old V2 one, still come back up, because all I did is rename the protocol. So for number 2, it's actually pretty straightforward. I can rename these interfaces. They used to be called XE1-1 for 10 gig Ethernet 1.1. And I now call it LCP DDLN1 because that's the router it's going to point at. And I'll take it unnumbered from loop 0, which allows me to remove the addresses. So I can test this and see what it might do in the data plane and then apply this config, and VPP will reload it. And then all I have to do really is move this interface from the OSPF4 old into OSPF4, which is the V3 version of it, and maybe give it the right interface name as well. So when I reload this, the adjacency moves, and now I see OSPF4 has that adjacency towards DDLN1 on a link local address. And I can also see that it picked up the IPv4 loopback address on .6 on interface, that's funny, 10 minutes, on interface DDLN1. Okay. So now I rinse and repeat. That was one interface. There's maybe 60. So I'll do them one by one, grab some coffee, just move from a couple of routers and links to like some routers and links in Zurich, and then upwards north on the ring and back down via France. So the result is that all of these links now have symbolic names. CHGTG0 goes to Gladbroek, CHRMA goes to Rumlang, and NLAMS goes to Amsterdam in the Netherlands. Trace routes, similarly as in the lab before, now just use the loopback address for V4 and V6, saving me in total, what was it, 27/31s. It's a small ISP, but still that's like half or so, or a quarter of my /24s now freed up for better use. So one more thing in the 9 minutes, I guess, that I have left is performance of VPP. Like, why would I even do this? I could buy a Juniper, although I have 13 sites and I'm very small, so I don't want to buy 13 MX204s. It's a little bit expensive, even on street price. But this Dell over here cost me 600 bucks, 600 euros for a Dell that is now 9 years old. So what I'll do is I'll create this lab setup with 3 Cisco T-Rex load testers. They generate load. That goes through a Mellanox switch, which runs Debian, by the way. No vendor OS at all, just Debian. And then at the bottom, you see this machine that is called the device under test. That is my E5-2696. It's a 9-year-old, I think, 44-core CPU. There's some RAM in there, and then the machine under test has 24 10 gig NICs, and the load testers each have 6. So the way you configure T-Rex now is they send traffic out on some port going through this cloud called the device under test, and you sort of expect the packet back on the other side. Otherwise, it got lost. And each of my load testers has a bunch of ports, and so they're happily sending a bunch of traffic through my VPP machine, hoping to see it back on the other side. And then I have 2 methods of load testing at IPNG. Method 1 is to use single-threaded VPP. It is a multi-threaded app, and it scales linearly, which I'll show. But in method 1, I only take one worker, and it's trying to do all the traffic it can. And I'll just bump up the traffic until it stops forwarding more, and then I know how many packets per second can this one thread do. And then method 2 is RFC 2544, where you just do a linear ramp up from 0 to line rate, and you see when does the device under test lose more than 0.1% of traffic. Okay, so the first method actually can use a textual user interface called a TUI, and it looks like this, except it's not orange in production. And in number 1, you see here these interfaces and how fast they are and how fast they're transmitting. In number 2, we see the packet rate and the byte rate, or the bits per second rate on the TX side. And then number 3 would be on the other side, what comes out of the device under test. And hopefully these 2 numbers line up, right? Otherwise, we're losing stuff. And shown here is 4 times 10 gig with 64 byte packets, the smallest we're allowed to send. And that is about 60 million packets per second, or 40 gigabits, and all of it comes out the other side. So we know that at least with one core, layer 2 cross connects, which is very cheap to do, copy the Ethernet frame from the input to the output interface and marshal it out again, does at least line rate, which is 14.88 million packets per core. So I fiddle with this a little bit more. I can measure how many CPU cycles does VPP take to switch one packet through the data plane. And on the top left here, you'll see this cheap L2 cross-connect at 1,000 packets per second. Takes me about 991 CPU cycles to switch one packet. But if I ramp up the traffic, it amorts a bunch of CPU caching and DDIO to allow it at 10 million packets per second to only take 140 cycles per packet. So it got almost 5 times cheaper. And if I do this through to the end, I'll see that in a layer 2 cross-connect scenario, it does about 15.3 million packets per second per core. And noting it has 44 cores. So this machine would roughly do 500 million packets per second. With MPLS, I do 10.3 million, IPv4 11.1, and IPv6 9.7. And noting that this is with a full table loaded on VPP. So method 2 is a Python script. I'll skip over it in the interest of time. There's a bunch of load tests you can do. When people have non-serious vendors, they will say we do up to 20 gigabits, and that's oftentimes because they send very large packets and therefore few of them. It's very easy to do. It's only 800,000 packets per second for a 10 gig link. And then all the way down at the bottom, more evil and evil along the way, the smallest you're allowed to send is 64 bytes, which is about 15 million. That's what I was doing before. So first I'll do 1 port. So this ramps up from 11 to 10 past 11, 100% line rate, that's fine. And then the iMix, which is a mixture of medium, small, and large packets, is also 100% fine. And then the 64 bytes don't exactly reach line rate, but they're pretty good. They do about 75% of line rate. Then I'll do 6 of these, 6 times 10 gigs bidirectional, which again, for large packets is easy, iMix packets is easy, and for 64-byte packets, we now linearly did 6 times 10 gigs at 72.5% or so of line rate. So it does regress a little bit for bookkeeping reasons, but it's roughly linear. And then my first claim is that this thing can do 100 gigabits, which it can, and in fact a little bit more than that. At 950 in this load test, where I just used 18 ports from 0 to 100% of line using this RFC 2544 load test, method 2, it'll do 100 gigs easy, and it goes up to 180 gigs, and there's no more capacity on the network cards, which is 14.7 million packets per second. By the way, this only uses 18 threads in the VPP machine. There are 44, so there are 26 left over that are doing absolutely nothing, 2 of which are for the OS. So I could use 24 more threads in the data plane. And also, unfortunately for me, and also for you, I guess, VPP had 24 NICs, but I only had 3 load testers, so I can only use 18. I guess it could have gone to 240 if I used a 4th machine. But it easily does 100 gigs. Now, 100 million packets per second is a little bit harder because now it actually has to do a lot more work. But it does this as well. 100 million packets per second at 1102 in this load test, and in total 165 million packets per second at roughly 150 gigabits per second using 128-byte packets, and ask me in the hallway why that is. Again, easily proving that this machine, which is a 10-year-old Dell essentially that costs 600 euro, will do 100 million packets per second and then some with MPLS, IPv4, and IPv6. There you go. Any questions? Or maybe no questions, I'm not sure.
Okay, thank you very much, Pim. Please stay. I take only 30 seconds. Sorry for Italian. Pim si fermerà a pranzo, quindi visto che comunque il cinema fa un po' fatica come location a fare domande e risposte, io vi invito a prenderlo poi a pranzo, chiedergli le cose. Thank you very much. From my side, also from the community, for Italian operator, for your work, your amazing work. I know that you know my network. And just say that we have just Snaquadria border router make with server, you know, and we will move to VPP, the whole Snaquadria infrastructure, I think, as soon as possible. I think it's on your roadmap.
You'll not regret that. That's going to be so great.
Yeah. So really, thank you. Thank you very much for your work. It's amazing work.
Thank you.
Thank you. Thank you.